Hi everyone, and welcome to the course on modular multi-level converters for medium and high power application. This is the fourth lesson of module 1 on basics of inverters. In this lesson, we will get familiar with the basics of operation of a three-phase DC to AC inverter, and we will start to also understand the basics of modulation, including a square wave modulation. Three-phase inverters are commonly used in applications such as AC motor drives to supply three-phase loads. This is the circuit diagram of a three-phase inverter. We have three phase legs. Each phase leg corresponds to one phase. On each phase leg, we have two complementary switches, similar to what we discussed for an H-bridge inverter. The objective of controlling this circuit is to control these 6 semiconductor switching devices in such a way that we synthesize controllable sinusoidal voltage waveforms at the AC side of the converter with controllable magnitude and controllable frequency. So, similar to what we discussed for the H-bridge inverter, we have a few modulation techniques that we use to control these switches and to synthesize the sinusoidal output voltages. The first technique is the square wave modulation. Similar to what we discussed for an H-bridge inverter, we implement the square wave modulation for a three-phase inverter as well. So the way we implement is that for phase leg A and switches S1 and S1 bar, we generate the gating pulses in such a way that the switch S1 will remain on for half of the output voltage cycle, and it goes off for the rest of the cycle. And switch S1 bar is complementary to S1, so its gating pulse will be complementary or inverted with respect to S1, as you observe on the plots representing the gating pulses for S1 and S1 bar. We repeat the same sequence for phases B and C. However, since we would like to synthesize three-phase balanced AC side voltages, we have to introduce the phase angle displacement between the three phases. So for phase B, as you observe, we have the same switching pattern for switch S2 with an additional displacement angle, which is 120-degree phase shift with respect to the gating pulse for switch S1. We do the same for switch S3. We introduce another 120-degree phase shift with respect to the gating pulse S2. And in this way, if you look at the three-phase system, they are displaced like a three-phase balance system in terms of phase angle. And of course, the gating pulses for switches S2 bar and S3 bars are generated in a complementary manner with respect to the gating pulses of S2 and S3. Now, if we switch these 6 switches in the manner described, we come up with voltage waveforms for the phase A with respect to the terminal N, B with respect to N, and C with respect to N, based on what you observe on this slide. And these voltage waveforms are very much similar to the pattern you see for the corresponding phase gating pulse pattern. So these are the phase terminal voltages. And now, if we want to look at the line-to-line voltages, we know that the line-to-line voltages can be obtained by subtracting the phase voltages. So here are the line-to-line voltages, which are concluded based on subtraction of the phase voltages that we had in the previous slide. So if we look at the line-to-line voltages, they are not sinusoidal waveforms, but if we start to look at each waveform and we look at Fourier series expansion, we come up a term to express the RMS value of the fundamental component of the line-to-line voltage, which is a constant coefficient times VDC. And since VDC is usually constant, we see that based on the equation, the fundamental component of the line-to-line voltage is constant, and we don't have any controllability over it. That's the problem that we had for single-phase inverters as well. If we look at the harmonic components, we see that each harmonic component in the line-to-line voltage, its magnitude is inversely proportional to the order of the harmonic, and harmonics are of the order of 5th, 7, 11, 13, and so on. And that's also the drawback of a square wave modulation for a three-phase inverter as well. Presence of low-order harmonics in the output voltages, and also having no controllability over the magnitude of the fundamental components. And as we discussed for the single-phase inverter, it's very easy for practical implementation, and the switching frequency of each switching device is very low. These are the advantages. However, having no controllability over the output voltage and also presence of low-order harmonics are the two major issues associated with this modulation strategy. If we look at the converter waveforms, we also sometimes need to look at the voltage of the phase terminal with respect to the load neutral point. And we need to come up with an expression for that as well. So the way we derive that is based on writing a couple of KVL equations in this loop, for example. So the first KVL is associated with the KVL in this loop. The second and third are associated with the similar loops for phases B and C. And this is IA, this is IB, this is IC, and this is which represents a three-phase balanced load. So since the load is balanced, and we know that for a balanced load, IA plus IB plus IC would be equal to 0. If we add these three equations together, this term would be cancelled out, and we come up with the value for the voltage of the load neutral point with respect to the capital N point, which is the reference point for our analysis. And we come up with this equation. Therefore, by replacing for V and N in this equation and replacing IA times Z, which is nothing but VAN, we can conclude the first equation here. Similarly, we can repeat the same procedure for the other two equations, and we come up with the expressions for the phase terminal with respect to the load neutral point in terms of phase terminal with respect to the point N, which is the reference. And by having these expressions, we can come up with the voltage of each terminal with respect to the load neutral point, which is a staircase waveform, as you see on this slide. So in this lesson, we learn about the circuit and basic of operation of a three-phase inverter. and we look at the simplest modulation technique for control of this inverter, which is a square wave modulation. To address the issues associated with the square wave modulation, in the next lesson, we will take a look at the sinusoidal PWM techniques to control this inverter. Thank you.